All right, so I think this is the 25th, 25th day of operations research. So what we did last time is we proved Sperner's lemma in one dimension. Okay? What was Sperner's lemma in one dimension? What does it say? What was 1D Sperner? You always have an odd number. So Sperner, one dimension. So we start off, here's 0, here's 1. And we put in some partition points. And then in the interior, we can label them 0 or 1 however we want. And the result is that there will always be an odd number of segments labeled 0, 1. And eventually, this is going to be used to show the existence of a fixed point for something later on. Now, the problem is we will have no idea where that 0, 1 segment is. This is going to be an existence proof, not really a constructive proof. Unless, of course, we actually go through and start doing the label. Okay. There is another way to do the proof. It's essentially the same as what we've done, but it's a different way of writing down the algebra, and this way is going to generalize a little bit nicer to what we're doing next. So let's revisit. So I'm going to let S00 be the number of 00 segments, hence the letter S. And then S01 will be the number of 0110 segments. I really don't care if 0 is on the left and 1 is on the right or vice versa. I just care the labels. And in a complete shocker, I'll also study S11. Okay? So we have three quantities. How many 0, 1 segments does S01 contribute? How many 0, 1 segments does S01 contribute? Well, we haven't proven that. That's what we're trying to prove. I'm really basically asking you what's the definition of S01. Right? S01 is the number of 0110 segments. So the number it contributes is just itself. It's just our count of how many there are. So if I had this as my label, 011010, this would be a 01 segment, so we would have 1 over here. We would have a 10, we would have a 01, a 10, and a 01. So we'd have 1, 2, 3, 4, 5, and thankfully that is an odd number. Okay? So in this case, S01 would be 5, S11, there's only one of them would be 1, and S00 would be 0. Okay? Let's think about the numbers 0. How many times are 0 counted in a 00 segment? So let's take a 00 segment. How many times will we count a 0 in a 00 segment? So here's a 00 segment. How many times do we count this 0?
Don't you just count the one on the left as 1?
We count it once in this particular segment. How many times will we count it as we go through the whole thing? If we are looking at how many zeros there are in the 00 segments, the 01 segments, and the 11 segments, how many times would this particular 0 be counted?
Twice.
Always twice? Unless it's at the end. So if we extend towards the left, if we still have points over here, then it doesn't even matter what label this is. This 0 is going to be counted twice, unless it's the leftmost 0, in which case it's only counted once. So if I add up these segments, will I get the number of zeros, or will I get one more or one less than the number of zeros? Or maybe off by a factor of 2. So I'm going to basically be double counting all interior zeros. So we could study S00 plus S01 plus S11. And so if we look at that sum, what are we going to get? This is counting the number of segments. Okay? Well, the number of segments is just going to really be easy. It's just the number of division points we've had. That's not a particularly interesting quantity to study. This is somewhat similar to when we were doing the infection game. Or was it the infection game? Yeah, the infection game. Trying to figure out what's the right invariant or monovariant to study. We could try to look at something like this, but this is not going to be a great quantity. It just counts the number of segments. But we want something related to this. So over here, we were talking about if we have an interior 0, it's counted twice. Once going to the right, once going to the left. The only 0 that's not counted twice is the 0 at the left endpoint. So what kind of relationship can you give me involving these segments and the number of zeros?
Is it 2 times that?
2 times the whole thing?
2 times the last 2 things.
2 times these two? Yeah.
I was going to say the first 2 divided by 2 and take the 7.
Okay, so we clearly don't care about the S11. That's not going to do anything in terms of counting the number of zeros in play. So when we're trying to figure out what we want to study, we don't need the S11 term. Let's say we count all of these. So if we have a segment that has a 0 in it, if that 0 is interior, it's actually part of 2 segments. If it's not interior, it's part of 1 segment. So if I add up how many segments there are, how is this related to the number of zeros? Yes?
I said that if you divide that into the 0.
So if we divide this by 2, I don't really want to take ceilings. I really don't want to take a ceiling. Not this early in the morning. But there's also something we have to think about. What's the last thing we have to worry about? Yeah, the n0 is only counted once. So let's just try to find a formula to count the number of zeros. Number of zeros. Each segment 0, 1, how many zeros does the segment 0, 1 contribute? It contributes 1. What about the segment 0, 0? How many zeros does that contribute? 2. We've counted every 0 twice except for 1 0. Which is the 1 0 we haven't counted twice? So if we add 1, this should be 2 times the number of zeros. Every 0 has now been counted twice. So it takes a while to figure out what's the correct object to study. These seem to be natural things to come into play. And so if we're looking at this, this is close to what we want. But there is a difference between the role played by 0, 0 and 0, 1. The hard part is really figuring out what is the object to study. And it takes a while. You play with it a little bit and you try to figure out what do I want to look at. The big bane in probability, the big thing you always have to avoid is double counting. On the flip side is not counting things enough. And so here we actually have both issues. We're double counting in a lot of places. So then we can say, oh, let's just double count everything. But if we double count everything, we forgot about the 0 at the end, which we only counted once. So now we look at the following. So is everybody happy that every 0 on the right-hand side has been counted exactly twice? Counts all zeros exactly twice. All right. Abstract algebra is not a prerequisite for this course, which is good because I've never taken it. How many of you have not taken abstract algebra? All right, good. I can't really yell at you because I've never done it either. all we need is basic results on clock arithmetic. So we just need to look at things mod 2. Is there anybody here who has not seen things mod 2? Okay, so all we care about is even, something, even, odd. So the only way this equation can work is if we look at it mod 2, is S01 must be odd. So mod 2 implies S01 is odd. Therefore, non-zero. Therefore, there is a 0-1 segment. So this is essentially the same proof we did last time. It's just writing it down a little bit more formally and trying to set it up in such a way that we can then extend the argument to higher dimensions. I'm only going to prove Sperner in 2 dimensions. Once you can do it in 1 and 2, the idea is clear as to how you would just keep building it up. You know, if you want to, it's a good exercise to just go through and do that. For those of you who are working on that chapter, what you should do is just make it a series of exercises. You know, it's not worth really writing up separately. Any questions on this? In an ideal world, we would have plenty of blackboard space, and I would just shove this up so we could keep this in front of us as we try to go to 2 dimensions. So instead of trying to count the number of 0-1 segments, what do you think we're trying to count in 2 dimensions? Yeah, which triangles? We don't, I'm sorry, this is not the politically correct America. I don't care about all triangles equally. I discriminate proudly. What is the only triangle I care about? I only care about the 0-1-2 triangle. I don't know how it happened, but this morning at breakfast, my kids got into a contest to see who could draw the acutest triangle. And it's tough to really yell at them to please eat your breakfast when they get into a contest to see who can make the smallest acute angle. So what do you think we want to have before? So, again, while we only care about the 0-1-2 triangle, we might actually have to deal with some of the other triangles as well. Just at the end of the day, we don't care what their values are. We only care about how many 0-1-2 triangles there are. So what do you think we should start with? We've got to introduce some notation. What quantity should we be studying? T, okay, good, T for triangle. Okay, so T what?
Do we need a T for every type of triangle?
Oh, good God, that would be a lot, wouldn't it? So how many types of triangles do we have?
3.
So I hear 8, I hear 3. One possibility is I have 3 vertices. Each vertex could have 3 labels, right? So if I just do it naively, that's 27. But then we could say, well, a 0, 1, 2 is the same as a 2, 1, 0. So maybe I want to look at how many different ways. I have 3 triangles that all have the same label. Then if I want to have, so if I want to do 3 where they all have the same label. If I want to have exactly 2 distinct labels, I have 3 choices for the first, and then 3 choices for the second. And then I have 1 way to have all distinct labels. So I think maybe 13 different triangles. I'm not really leaving that much space on the board. So I probably don't want to look at 13 different triangles and deal with all those cases. Right? Let's think about what's going on. Here's 2-dimensional Sperner. Here's 0, 1. This is 0, 1 land. Okay? This is 1, 2 land. And then this is 0, 2 land. And then it doesn't have to be a regular triangulation. I think everything is a triangle. I don't think I've screwed it up. Okay. we want to somehow build on one-dimensional Sperner, right? There's probably a reason why we started with that. So we want to somehow use what we know and build up. What do we know from one-dimensional Sperner?
We could apply Sperner to the bottom.
So we could apply Sperner to the bottom. So good. So we know something about the bottom. What do we know about the bottom? There's at least, I'm sorry? There's at least one 0, 1 segment. So by 1D Sperner, there exists a 0, 1 segment on the bottom. Our goal is to try to get a 0, 1, 2 triangle. This is a pretty good start. So this might give us an idea of what kind of triangles we should look at. Which triangles do you think we should look at? I'm sorry? Well, if we look at ones on the bottom, I can easily maybe jerry-rig things to destroy you. The goal is that if you look at enough triangles, there's nothing I can do to stop you. You will have to get a 0, 1, 2 triangle. But if you just keep yourself locally down on the bottom, I might be able to thwart you. Yes?
You only look at triangles that already contain one of those.
So what if we, instead of looking at all, was it 14? Instead of looking at all, or 13? 13. Instead of looking at all 13 triangles, what if we only look at triangles that have a 0, 1? How many triangles are there that have a 0, 1? Only 3? Oh, good, and I have enough space to do 3 things here. What a wonderful coincidence. So T 0, 1, 2 will be the number of 0, 1, 2 triangles. I hope the notation is clear. The next one would be T 0, 1, 1, and then T 0, I guess 0, 1. It doesn't really matter which order you write them. It will be the number of 0, 1, 1 triangles, and this will be 0, 0, 1 triangles. Are there other triangles at play?
Are we counting zeros again?
That seems like one of 2 things we could do. One of 2 things we could do is we could count zeros. What else could we count? I am deliberately not telling you what I want to count. So one possibility is we could count zeros. You know, we counted zeros before. Let's keep counting zeros. What else could we count? We could count 2s. What else?
0, 1 segments.
Or we could count 0, 1 segments. So we have lots of different things to choose. You know, whenever you come to something like this in math and you're not sure which way to go, take 3 pieces of paper. Here's the 0 paper, here's the 2 paper, here's the 0, 1 segment paper. And try one of the approaches for a while. And if it doesn't look promising, if it's not going anywhere, put that paper aside and go back to one of the others. Which do you think we want to count? The number of zeros, the number of 0, 1 segments, or the number of 2s? I feel like Monty Python 3 is right out. Which makes sense because there's no 3's in the problem. What do you think? Do you want to count 0, 1 segments, or do you want to count zeros? You don't have to vote for what you've suggested. Anybody want to give me a reason to study one over the other? I've read the book would be a good argument. This is actually a good moment for one of my favorite quotes. How many of you have ever seen the movie Patton with George C. Scott? He actually was given, I believe, a Academy Award and Oscar for his performance and declined it. My father's dentist served with Patton, and he said that George C. Scott did a better Patton than Patton did. You know, Patton wished he could act like that all the time. It's a terrific movie. There's one scene early in the movie where the American Expeditionary Force has already been defeated by the Germans. Patton comes in as the new tank commander and faces Rommel's forces in the field and routs them. And the beautiful line is, "Rommel, you magnificent bastard, I read your book!" So after World War I, Rommel wrote a book on tank tactics. It was a really good read for Patton to read how Rommel thought tanks should be used in battle. So I strongly recommend either reading Rommel's tank tactics book, it's in German, but I think it has been translated, or reading ahead in the textbook to get a sense of what we might be discussing. Because this would be a really good opportunity for you to say, well, let's see, I think I know because I've read the proof. So I know which one we should be looking at. What do you want to try?
Counting the number of segments.
Okay, why do you want to try counting the number of segments?
Because it seems like we're moving up a dimension.
So it seems like we're moving up a dimension. So let's try to count the number of 0, 1 segments. Wait, I'll leave this 2 times the number of zeros. So this is what we had in 1 dimension. Let's try to count in higher dimensions. Let's count the number of 0, 1 segments. If we have an interior triangle, let's look at the interior first and then worry about the other stuff later. How many does T012 contribute if it's interior? 1. So T012 contributes 1. Okay? What if it's exterior? How many segments does it contribute? It's still 1, right? The triangle itself always contributes 1 segment. What changes is how many times that segment is counted. If the 0, 1 segment is interior, how many times do we count it as we go over all of our triangles? Twice. If it's on the outside, it's got to be down on this line, and we only count it once. So what we're going to be getting into a situation again is we're going to get twice the number of 0, 1 segments. So any interior segment is only going to be counted once. Any interior segment is going to be counted twice. Any exterior segment is going to be counted twice. No, sorry. Any interior segment is counted twice. Any exterior segment is counted once. The triangles T012, they only give you 1 segment. What about the triangles T011? So we have a 0, 0, 1 triangle. How many 0, 1 segments does that give you? 2. And I did 0, 0, 1. Sorry. And then the last one is going to be the T011 triangles. And how many segments do those give? 2. So that counts every interior segment twice. And the exterior segments, how many times have we counted those? Once. So now, this is the nice thing about having a very long blackboard. Let's add in S01. And that's going to count the number of 0, 1 segments on the boundary. Do I have to worry about all 3 boundaries? No. I forced the label 0, 1 to only be on the bottom. So there's no 0, 1 segments anywhere else. So this contributes 1, this contributes 2, this contributes 2, and each one of these contributes 1. And now we've counted every segment twice. So interior counted twice, the need S01 to count external twice. Okay? Does this seem reasonable? Well, if we've counted everything twice, the left-hand side is an even number. And now look at how beautiful the right-hand side is. It's a little bit longer than before, but twice even. Twice even. And we know from 1 dimension that this is odd. So look mod 2 as S01 is odd. This implies T012 is odd. Therefore, T012 is greater than 0. Or if you want, greater than or equal to 1. And that's the proof. This proves the existence of a 0, 1, 2 triangle. No matter how we choose the points. So let's say I actually give you a triangulation. You know, I give you a bunch of interior points and I break this down into a triangle. And I want you to give me a strategy that will guarantee that you will construct a 0, 1, 2 triangle. What would be your strategy? Can you give me a constructive strategy? This proves that it's possible to do it. Yes?
Doesn't it also prove it's impossible to not do it?
It is impossible not to do it.
And then just don't say anything?
Well, I want you to have it, so
So just keep labeling them and you'll just go.
keep labeling legally.
Yeah.
Choose any legal labeling and you will have one. If you wanted to do it really explicitly, what you could do is you could say, I'm going to start here and I'm going to do all zeros down here. So I will have a 1 and a 0 over here. If I try to do all 2's up here, notice I don't necessarily have a 0, 1, 2 triangle. However, you know, if you really want an easy strategy, if I put a 0 immediately to the left of 1, this is one side of a triangle. There's got to be another vertex. What should I label that vertex? 2. So I mean, if you want an explicit strategy, it's possible to get a very explicit strategy. You know, choose immediately to the left of 1 as a 0, look at the third vertex in that triangle, put that as a 2. But no matter what you choose, you will always get such a triangle. Okay? I'm not going to generalize this to higher dimensions, but we could try to go up to like a tetrahedron. Why do you think the tetrahedron would be the shape we would want next? So why a tetrahedron? Has 4 points, you know, the 0, 1, 2, 3, so it's the next. But there's lots of different shapes I could have done. What's the advantage of having the shape of a tetrahedron? Or a pyramid with the triangle base? We can go down a dimension, right? How did we prove Sperner in 2 dimension? We proved Sperner in 2 dimension by doing some stuff in the middle and then saying, well, we know what's going on this edge. We know there's an odd number of segments that are 0, 1 here. So if we now try to go to Sperner in higher dimensions, we want a 0, 1, 2, 3, right? And so if we build up from a triangle, then we'll have something about this triangle down here. So in this triangle down here, we can only use 0, 1s, and 2s in the labeling. And what do we know must be true? It's an odd number. It's more than there has to be. That the number of 0, 1, 2 triangles down here is odd. So when we start building it up, over here we were looking at triangles that had a 0, 1 segment in it. What do you think we would be looking at for the next one?
A 0, 1, 2 triangle.
Not a 0, 1, 2 triangle. We're going up a dimension now. What do you think we would want to be looking for next? Tetrahedra. Tetrahedra that start with a 0, 1, 2. And then how many different things would we have to play by putting in at the end? Possibly 4. Okay? And you should be able to see the induction, you know, beginning to form now. And hopefully you see it well enough that there is no need to actually codify it and write it down explicitly, that this is enough to get a sense of what's happening. Okay? And so that there will be something like this. Okay. Any questions? Yes?
So in nth dimension, we would just be looking at like an n simplex?
Yes.
Okay.
And what we're really going to be doing when we're trying to prove our fixed point theorems is we're going to say it's enough to be looking at mappings from like a simplex to a simplex. Okay. All right. So this is Sperner's lemma. The main thing is to make sure we do Sperner's lemma in one lecture. I really don't want to split up, you know, counting triangles and whatnot into 2 different lectures. So this was the main goal for today. We now have a little bit of extra time in terms of what we do next. So one thing is, if you want, I'm happy to review a results or two from real analysis before we continue. Is everybody happy with real analysis? Do you want to see like a proof of Bolzano Weierstrass? You have to speak up, unfortunately, to say so. People comfortable with their real analysis, or do people want? Okay, so you are excused from one homework problem for speaking up. When I taught differential equations years ago, I think I told you 43% wanted to see a review, and no one was willing to speak up, but they did it with clickers. And so I told them, I will not publicly say in this class how many people want to, but I never said I wouldn't say it in different classes. And so 43% wanted to see a review, and not one person was willing to ask the question. Okay, so Bolzano Weierstrass. So there's lots of different ways you can state this. Let me just see which one I'm doing in the book. Okay, so I'm doing S is compact subset of Rn. Oh, I thought you didn't like that it was a compact subset of Rn. Xn goes from 1 to infinity is a sequence in S. And then there exists a subsequence that converges to an X in S. Okay, this is one of our main types of existence arguments. So whenever you see an argument, or whenever you see a theorem, you should always remove a condition. What should happen if you remove a condition? It should either no longer hold, or the proof is probably harder. It's not necessarily the case. Sometimes, by putting in additional conditions, the proof is harder because you're using things you shouldn't use. So I'm going to do a little aside right now before we prove this. How many of you know what a transcendental number is? So a transcendental number is a number that is not a solution to a finite degree polynomial with integer coefficients. Square root of 2 is not transcendental. It's an algebraic number. X squared minus 2 equals 0. I is an algebraic number. X squared plus 1 equals 0. I is a solution to that. A lot of the numbers we know are algebraic numbers, but there are some numbers that are transcendental. Can anybody give me a transcendental number? You don't have to give me a proof. Yes. E. Another transcendental number. Pi. And it'll be interesting to see what order people choose E and pi, as to which one do you list first. These are both transcendental. Does anybody know a relationship between E and pi? It's one of the most beautiful relationships in all of mathematics. Say it again? Okay. You said plus 1? Okay. You can either do it with an addition, or you can say it equals a negative 1 and just cut down a little bit on symbols. Either way is fine. So this is a great relation connecting E and pi. All right, here's the theorem. Either E plus pi or E times pi is transcendental. What order did I use? Nope. Inclusive. We actually believe both of them are transcendental. We can only prove that at least one of them is transcendental. Do people want to see the proof, or do you want me to go back to Bolzano Weierstrass? Proof. Okay. What do you think is going to be a key ingredient in this proof?
The formula you just wrote.
All right. How many people think we need to use this in some sense? Good. Congratulations. You've all been led down the wrong path. That formula has absolutely nothing to do with the proof. And that was the whole point of this digression, is to show you that when you know too much, as the students in my probability class found out with the Skynet problem, you could be confused as to what is going on. Yeah. Kim and Kayla destroyed a lot of my students on that one because they were not confused by all the fluff going on and all the red herrings. This is a complete red herring. The result is the following. Let T1 and T2 be transcendental numbers. Then either their sum or their product is transcendental. It has absolutely nothing to do with the fact that they're E and pi. But when I say E and pi, your first thought is, okay, well, what do I know about E and pi? How can I use that in the proof? This is sometimes the danger. And again, this is a post-core class. The goal is not to just regurgitate proofs in the book. The goal is to talk about how do you come up with proofs. When you do not know how to come up with a proof, when you do not know the right path, you have to figure, well, what tools do I use? You can easily be misled and try to use facts that don't really matter. So we need the following stuff, and if you haven't taken abstract algebra, I apologize, some of the stuff is not going to make as much sense. So algebraic number solves a finite polynomial with integer coefficients. And we have the following fact. If alpha 1 and alpha 2 are algebraic, that implies alpha 1 plus alpha 2 and alpha 1 times alpha 2 are algebraic. For those of you who've taken abstract algebra, what would you say about the set of algebraic numbers? It's closed. Okay? I'm not going to prove that, but it seems reasonable that I should somehow be able to find a way to combine these polynomials and get it to work. If you're looking at field extensions, I basically have a finite field extension of a finite field extension is a finite field extension. Okay. So assume T1 plus T2 and T1, T2 are both algebraic. We're going to get a contradiction. I claim that at least one of them is transcendental. Let's get a contradiction. All right. What can you tell me about T1 plus T2 squared? Algebraic. It's an algebraic number times an algebraic number. What about 4T1, T2? What can you tell me about this number? Algebraic. 4 is an algebraic number. It solves the equation x equals 4. Okay? All rational numbers are algebraic. Any idea what I should do between these two numbers? I think you did it, yes? What should I do? Subtract. Or if you want, multiply by -4, which is algebraic, and then add. All right? So the difference of algebraic numbers is algebraic. This is equal to T1 minus T2 squared, which is an algebraic number. I claim the square root of an algebraic number is algebraic. Just take the polynomial and replace all of your x's with x squareds. And that will give you the square root. Square root of algebraic is algebraic. Therefore, T1 minus T2 is algebraic. But by assumption, T1 plus T2 is algebraic. And so if we add them, what do we get? So we get 2T1 is algebraic. Therefore, T1 is algebraic, which is a contradiction. Okay? So sometimes when you look at extra properties, it can mislead you in terms of how to approach the problem. Yes?
How is that a contradiction when we're saying that T1 plus T2 is algebraic?
Well, T1 and T2 are two transcendental numbers.
Oh.
So we're starting off with two transcendental numbers. And then we're proving that at least one of these. Yeah. So all we know at this point is one of them is transcendental. Since then, in fact, what this tells you is if you know two transcendental numbers, you can construct infinitely many transcendental numbers. You just may not know which ones are transcendental. Well, one thing is you could do stupid things. You could do pi, 2 pi, 3 pi, 4 pi, 5 pi. This is a little bit more interesting. Pi plus e, e times pi. There's a lot of great stuff on transcendental stuff like this. So the reason I'm doing this is just the warning from real analysis. So Peter Jones was my professor at Yale for real analysis, outstanding teacher, and he really hammered home, whenever you have a result, you want to remove a condition. And either the proof is harder, or there's a counterexample. Sometimes it fails. The other really good advice he gave me, and this only works the more math you've done, is if you've never heard of the result is probably false. By the time you've done math for many years, by the time you've read 6 or 7 different books on real analysis and abstract algebra, if you haven't heard of something, it's probably not a correct reformulation. So there's lots of different ways of defining what is a group. And on my general exam, I was actually given a new definition. It had left inverses, I believe, and right identities, I think something like that. And it was not an equivalent definition. It actually did not lead to a group. And so, I forget exactly what it was, but when I was given it, I said immediately, this is not an alternative definition of a group, because if it was, I would have seen this in one of the exercises in one of the many algebra books I looked at preparing for my journals. I've never seen this as an equivalent definition. It must be false. I said, great, now find a counterexample. And you find one very quickly looking at 2 by 2 tables. So let's remove a condition. So compact means closed and bounded. So let's remove bounded. So what's a counterexample if we remove bounded? And let's just look at the real line R. If we can do things in the real line, we can do things more generally. So what would be a counterexample? I want a sequence that does not have a convergent subsequence in R. Natural numbers. xn equals n. Question? Or?
Yeah, sorry, what is the word underneath then?
Converges. So xn equals n. You can either be excited, and the exclamation point can be for excitement, or it could just be for the factorial. Either one works. All right, remove closed. Would be a counterexample if we remove closed. So now, give me an interval, give me a set that's not closed.
X greater than 0, less than 1.
Okay, good. So we can take like the open interval 0, 1. Give me a sequence now in the interval 0, 1 that does not have a convergent subsequence. So I want a sequence of numbers in 0, 1 that does not have a convergent subsequence to something in 0, 1, in the open interval 0, 1. 1 over n, sorry. So 1 over n does have something that converges, but it doesn't converge in the open set 0, 1. So if I remove either of these conditions, if I remove that S is closed, if I remove that S is bounded, we have counterexamples already. So it's essential that we have closed and bounded. So when we were doing our first fixed point theorem, and we were talking about, did we need the space to be compact or not? It turned out in the end we didn't. It was merely for convenience, maybe almost like a security blanket, to assume we were working in a compact space. Did not need it. Here, we can see that this is absolutely essential. If you haven't seen looking at theorems in real analysis or theorems in other subjects like this, I strongly recommend this method. It's a great way to build intuition and really see what's going on. Drop an assumption and see what happens if you drop that assumption. All right, so now let's take S closed and bounded. Okay? Normally, people just prove things for S equals 0, 1. I'm happy to do it for S is 0, 1. If not, I'm happy to do it for a more general compact subset of 0, 1. What do people want? 0, 1. All right, so we'll do it for 0, 1. This is be nice to Professor Day. Thank you. So here's 0, 1, and this is S. If you did not give me 0, 1, if you gave me just a more general compact subset, a compact subset is bounded. So what I can do is I can intersect it with a ball of a given radius. And then the argument would apply essentially the same way. For ease of convenience, I'm happy to do this. We did divide and conquer in this class. That's essentially what we do right now. The proof is by divide and conquer. Put in the midpoint. We have an infinite sequence. Is it possible that we only have finitely many terms in both sides? No. So at least 1/2 has infinitely many points. And if you want, you can include the point 1/2 in both of them. All right? So at least one of 0, 1/2 and 1/2, 1 has infinitely many of the xn's. Right? Let's say it was this one over here. So what we're going to do is we're going to choose the smallest n such that we're in this. Choose smallest n such that xn is in 0, 1/2, the infinite part, the 1 or a1 with infinitely many. Call this n sub 1. Okay? Now we do the lather, rinse, repeat. We now chop this in half. And let's say this time it was 1/4, 1/2 that has infinitely many. So now we choose the smallest n such that it's in that one. And n2, that's going to be our n2, has to be greater than n1. So we have xn1 is in the interval 0, 1/2. xn2 is in the interval 1/4, 1/2. And n2 is strictly greater than n1. xn3, let's say it's in the interval 1/4, 3/8. And n3 is greater than n2. And so on and so on and so on and so on. So we're almost done. We now have a sequence of points. We have a natural candidate. So does the limit of x and k exist? And is it in S? Well, if the limit exists, it's clearly going to be in S. Why? Completeness. Right now we're looking at subsets of the reals. We're looking at we're looking at a compact set. In this case, every term xn is greater than or equal to 0, and it's less than or equal to 1. So even when you take the limit, it's going to always be there. So if the limit exists, it's clearly going to be in S. So now the only question is, does the limit exist? So why does the limit exist? Which result from real analysis? Yes?
Isn't the sequence going to be Cauchy?
Yep, sequence is Cauchy. So the Cauchy criteria. Or probably criterion, my Latin's not so good. Right? You can also start proving results. We have all these different subsets. Each one of them is contained in the previous. The length of each one is half the previous. If you look at the intersection of all these sets, it's going to just be 1 point. And so you have a lot of different results in real analysis where you do stuff like this. Okay? So it's not bad to every now and then just go back and revisit some of these proofs in real analysis, because we are going to start to need some of these results as we get into the proof of the Brouwer fixed point theorem. This is one of the big results in the subject. Okay. Have a good homecoming. Go teams.